when the porosity of the concrete is big. If we have a silica source, for example, like a reactive silica contributed by class F or class C fly ash, actually we don't have to worried about that as long as the consolidations, the compaction of the concrete is very well, and also we sure that our concrete is very dense, and then of course, carbonations, because of the moisture coming into the concrete, will be tackled or handled by the silica source or the CHS formations, secondary CHS formation in the pores. So as we have denser pores, we don't think that the carbonation becomes a great issue actually to enter the rebars. Some research already shown that the carbonation can be laminated layers to the concrete. So we have like naturally laminations because of the carbonations product, calcium carbonates, calcium coming from the surface of the concrete, and then together with the presence of the moisture, it can become a very good layers. And instead of be worried about the carbonation enter to the rebars, actually our concrete will have a very good cover because of the laminated system. Yeah, I think that's all from me. Maybe it can answer the questions.
Yes, thank you. Yes. We also in Japan discussed this kind of point. Of course, carbonation can be proceeded when we use fly ash. However, as Yani-san said, also importance of water penetration and so on. Then, if pore structure is okay, it will be durable. And also, experiment, we always shorten or accelerate carbonation. That is actually different from the reality, I think.
Yes. That's right.
Okay, it's okay. Thank you. Okay, thank you. Yes. So actually, next presenter, we have the Dr. Takeshi Yamamoto, but due to the problems of the internet, so I would like to change the order of presentation from Japan. So the next is change the change to the Dr. Torichigai from the Dr. Yamamoto. Then I would like to invite the presentation of Dr. Torichigai. Then after that, the time for Dr. Torichigai, I would like to ask the Dr. Yamamoto. So in the next session. So Dr. Torichigai, sorry, the sudden you are not our notice, but could you share your screen at the start of your presentation?
Thank you, Dr. Yamamoto Sensei. Thank you for giving me such an opportunity. Okay. Yeah. Okay. Thank you for giving me such an opportunity, and I'm appreciated to the chair for JSCE and I'm Takeshi Torichigai. Please call me Takeshi. I'm a chief research engineer of Kajima Corporation. Kajima Corporation is a construction company in Japan, and I'm researching about the concrete engineering. So the Kajima Technical Research Institute in my company. I'm in my yes. So today I'd like to about make brief the introduction of Kazuma, and I focus about the concrete dam and the dam concrete using fly ash in Japan. Almost all dams use fly cement in Japan. So how to use fly ash for the dam concrete and the property of the dam concrete using fly ash and benefit and co-benefit. I'll explain about it. So brief introduction of Kazuma Corporation is the headquarters of my company is Tokyo, Japan, and just a moment. Pardon? Oh. Okay, just a moment. Can you see the slide? Anyone? Please. No? Haven't I? Okay. Yeah, that's okay. So my company is okay. You want the chat? Okay. Hi, okay. So the headquarters of my company is Tokyo, Japan, and the of my company is civil engineering construction, division construction, real estate development, and design engineering, and so on. This slide shows the history of my companies. Our company, Kazuma Corporation, is established in 1840, and our mission is leading the industry by construction in Japan and the world class. That's my mission. And paid capital, our revenue is this slide shown. And employees almost 20,000 people. And this number includes both domestic and overseas. And in Thailand, the Thai Kazuma is a group company of my group company. So we combating this. Converting all phase for the project, our company. So during all phases, not only for construction, but from early planning and design to maintenance, all phase our company's works. Okay. Then from there, first I introduce about the construction method of the concrete dam. So this figure shows the dam construction site. So I worked at that site, dam construction site, for 3 years, and I'm doing about the quality control of the concrete. So the river flows these lines, and the black triangle is dam construction site. So it is impossible to construct a dam river road. So because we dig a tunnel at first and change the flow of the river, and we constructed dam site. So this is called commutation. And then commutation and excavation the rocks, and then concrete construction is started. At the dam concrete, almost the concrete is separated into almost two areas. One is the outer part, other is the durable concrete is casted because of this area is the surface area. And so compressive strength and durability is required. On the other hand, inner part of the concrete is not required many compressive strengths. So the most important thing is reduce heat generation. So for example, the big size dam, RCD, roller compacted dam concrete is used also in Japan. About for the height of the concrete dam, the height of the dam is over 50 meters. We use the RCD concrete in the dam as an internal part of the concrete, dam concrete. The strength of concrete is 0, and it's so very hard. And water cement ratio, water binder ratio is 65 to 80% almost. And unit weight of binder is 120 almost to per cubic meter. So the concrete, the dam RCD concrete is very hard. So we transported by dump truck like this. And then spread with bulldozer almost 1 meter height at one layer. So many layers are spread in the dam concrete. So my work site, my dam is about the height is about 100 meters. So 100 layer is spread in the concrete dam. So this shows outer part of the surface area of the concrete. So the slump of the concrete is 3 centimeters, and the water cement ratio is almost 45 to 55%, transported by cable crane and compressed with very big by weight like right photo. And then how to use fryers for dam concrete. As Warren said, this slide shows the quality standard of fryers, Japanese industrial standard JIS. The SiO2, moisture, rigorous, and density, fineness, flow, activity index, these target value are decided under in Japan. Fryers is separated into 4 types. So and almost all dam concrete used is used type 2 fryers. And then in addition, most of construction site, in addition to JIS standard, detailed rules for fryers is decided. For example, this slide shows my experience at the dam site. For example, specification document for dam construction. So for a specification document for fryers quality, target value and allowable fluctuation ranges must be set for the following items. So such as SiO2, loss, and fineness. I just sorry. JIS standard value is here, and but we are required the target value and the ranges. So it's so strictly quality control is required for our company and also a contractor or a cement manufacturer. Okay. Lastly, I explained about the property of dam concrete using fryers. So this is this line shows the mixed proportion of our site, dam site. Example of Gokayama Dam. Yeah, that is Fukuoka. That is building Fukuoka in Japan. A number A is outer of concrete. So WY water by the ratio is 53.2, and the fresh content is 30%. And using cement, other cement, moderated Portland cement. So we call this type of cement we call MF20 or MF30. And outer part is durable concrete is needed, so unit weight of binder is 220. And on the other hand, LCD inner part of concrete 130 kilogram per cubic meter is used. And no slump concrete, so we estimate the press property by VC value. What is the VC value? This is this slide shows the VC value. That is arranged the VV test for RCD. The construction site, dam construction site, often uses gravel. The maximum size is 80 millimeters or 150 millimeters. In our site, the maximum size is 80 millimeters. So we're screening 40 to 80 millimeters of gravel and put the weight on the top. This is a weight. And shaking the lower table and measure the time until the mortar comes up on the slit. So this is a VC value test. So we estimate the quality, press property of the concrete, dam concrete, like these tests. And this slide shows comprehensive long-term compressive strength development of dam concrete. I know almost people to research the concrete, fresh concrete, as you know. So this shows explosion of A and number A and the number B2. So these concrete are the same as the maximum size of gravel and type of cement and the slump and the air content. These are same. And only W by D, water wind ratio is changed. So we often estimate concept strength at 91 days, and then as you know, from 91 days, compressive strength increased for 2 years and more. So, and water wind ratio is high. The increase is more high. So this B2 number B2 W by C is 75%. The compressive strength from 91 to almost 2 years, double. So on the other hand, we try to check the adiabatic temperature rise of dam concrete. This rise, so red line shows examination data of M20. And so use of fryers reduce temperature rise, so about 20 degrees Celsius, but is it converted saturated or not? I don't think saturated. But in the regression equation, like the blue lines. So in the regression equations, the temperature rise converges in about 14 days. That is estimated. So we use these equations as when we try to thermal stress simulation, thermal crack simulation, or thermal stress simulation. So that is consideration. Compressive stress for of dam concrete using fly ash increases over several years, but temperature rise of the concrete converges over 14 days. That is consideration. So we try to study about the real adiabatic temperature rise of dam concrete using these equipment. The heating engineering materials and the sealing container and the concrete. We put the concrete and the seal and measure the inside of the concrete temperature, and then we try to simulate these equipment and in the thermal analysis. We try to thermal analysis and this we get this adiabatic temperature rise of fly ash concrete. Black line is a conventional data, and red line is we get this study we got the data. Some concrete using fly ash may keep to generate a little heat in the long term, I think. So finally, this is a thermal analysis about concrete dam using different adiabatic temperature rise data. This figure shows the using conventional data. So we usually use these equation, this data, and this value shows the maximum degree maximum temperature at some points, and then we try to use this adiabatic rise, temperature rise data to the dam concrete. It's more about 10 degrees Celsius rise compared to the conventional data. So what indicates this? I think more cracks will occur at the dam concrete. So what at our site, inspection gallery is here, and the cracks I have never seen is occurred at this area. So that is due to that may due to the low heat, but the construction speed is very high. So concrete is covered. So because temperature is trapped and that inside, I think. So that's the conclusion of my presentation. In Japan, fly ash is used under the strictly controlled the concrete dam, and the compressive strength of concrete using moderate heat fly ash cement increases over the long term. And this is most of all you know, I think. But if construction speed increases and the heat radiation is reduced, heat may accumulate in the dam. So I think so. So that's the end of my presentation. Thank you for attention.
Thank you very much, Dr. Torichigai. Okay, so we would like to move to the Q&A session. Little bit time is over, but I would like to little bit short on the break time, about 10 minutes. So now I would like to ask audience to give some question and so on. But this means so. I would like the audience to give some question using Q&A system, because if you have some speaker problem, it's something not so good. So, and then now we have some question from audience. Then I'm not sure you can see the question here. I'm sharing, but it looks not work. But anyway, I summarize firstly, audience from a question from audience. First question and the second question related to the mechanical property of fly ash concrete. So one is elastic modulus, Young's modulus, and also Poisson ratio compared to the OPC. Dr. Berlangganan, can you answer that question?
Okay, for the mechanical properties of the fly ash concrete and when we compare with OVC, you can get the similar properties. I mean the mechanical property based on your mixed proportion. You can decide.
Okay, thank you. Then other question is to the Dr. Yanis-san, related to the geopolymer. Do you measure shrinkage of the geopolymer? Because someone asking wondering geopolymer has a high shrinkage, and also they want to understand so geopolymers concretes potential of corrosion of steel. So Yanis-san, could you answer this point?
Okay, thank you very much for the
Shrinkage
question.
and corrosion resistance. Okay, geopolymer.
Yes, okay. For the first questions related to the the shrinkage. Some people say that the shrinkage of geopolymer is very large, and some people say that the geopolymer shows a very low shrinkage, and we have found that depends on the quality of fly ash. Here in Indonesia, we have a kind of fly ash from different boilers. For example, like pulverized coal combustion boilers that burn the coal up to or more than 1,000 degrees Celsius. So it produces a high quality of fly ash. And the dissolutions of fly ash in the alkali system is really good. And this kind of fly ash will show better, I mean like a lower shrinkage. However, depends on the mixed proportions. It is kind like if we use a lot of liquid in the conventional concrete, shrinkage will occur or shrinkage will be very much controlled. For example, in a geopolymer system, the binder is the precursor or the fly ash, and the liquid is the alkali. If we put a lot of alkali, and then there is no way for the alkali to dissolve the fly ash particles. That's way we will find a very high shrinkage. But if we increase the amount of the fly ash and decrease the amount of the liquid, of course, shrinkage will not be a very much problem. However, workability will be a big concern because we don't use water. We don't use water, but we use the alkali, which has a density more than water. So because of that, it is like plus and minus positions. Like you want to increase the alkali system, you want to increase the workability. At the same time, increasing the liquid means that you will increase also the shrinkage. So until now, we cannot find any good super plasticizer, especially for geopolymer. The super plasticizer for conventional concrete sometimes doesn't work for geopolymer. So I heard that in Yokohama National University, the group of Professor Fujiyama Chikako already published some articles related to self-compacting geopolymer concrete. And she showed that there is no big concern on the shrinkage. So the first one, again, I emphasize the first one is the quality of the fly ash, and the second one, the ratio of liquid to the binder. And the second questions related to the corrosions.
Corrosion, yes.
Corrosions, yeah. Sodium hydroxide is the alkali that is very corrosive. Usually, it is very difficult for us to cast the geopolymer concrete without using the gloves or goggles, some, like a safety uniform in laboratory, because once it contact with the eyes and also contact with the skin, it will be very much, irritation, yeah. And then because of that, we understand that attaching the metals equipment directly to the sodium hydroxide should be avoided. So in the field, people usually use water first to the concrete mixer, and after that, just for making a moisture. Some moisture to the mixer, and then put the cement and fine aggregates and coarse aggregates, and finally the water. But for geopolymer concrete, we cannot just pour our metals equipments with the sodium hydroxide. It is prohibited. So we have to change the sequence. We have to put the fly ash first, and then after that, we put the alkali. However, after mixing with the fly ash, sodium hydroxide will dissolve the fly ash and the pH drop. And there are a lot of publications, there are a lot of reports say that pH of geopolymer is lower than pH of the conventional concrete. I think I have shown it in one of my slides. So there is no problem for using geopolymer based on sodium hydroxide or potassium hydroxide if we have rebar inside the concrete. And as also I already explained that the bonding system, the bond strength of a geopolymer is better than conventional concrete. So there is no problem with using the rebars inside the concrete. Thank you.
Thank you very much. Okay, thank you. Next is it's a question to the Japanese side. First one is how Japanese government encourages the use of fly ash concrete in private projects to the, for example, Kajima and so on. So, Dr. Toichigai, could you answer what his opinion? Government promote the private company to use, or I'm not sure.
No, I don't know about the government promotion.
How about Dr. Yamamoto?
Partly, the government or public committee requests to use French, especially at the constant construction of the downside. It's better to use the French to prevent cracking. But on the other side, private company does want to also use the flash. So in this case, Dr. Toichigai's presentation, the company will use why they're the same.
Yeah. By
yours.
Yes, I think so. Yes. So almost the government recommend the fresh use is durable to make a durable concrete for long-term durability is very good. Recommend, but as I know, so possibly, not possibly. So that just
not
recommended.
obligation. It depends on the company decision.
Yes, I think.
Okay, thank you very much. And the next one is how much prior stock availability in Japan. So Dr. Yamamoto, you know this one?
Yes. Now, it's about 10 million tons per year. The total amount of fresh is yielded. But in the future, for especially 10 or 20 years later, near future, in Japan, we will shut down the half of the coal power plant, maybe, in my sense. In that case, the total yield amount of fly ash will be about 5 million tons. And there's also a big problem about the quality of the fly ash. In Japan, we will use not only the coal for the fuel, but also we use biomass combustion. So we need to research about the change of the quality, chemical and the physical quality of the fly ash for uses of the concrete admixture. And also we must change the Japan industrial standard to use fly ash as an additive, concrete additive. So there's a problem, but in my sense, we can hold the total level of the fly ash for the admixture in about 1 million tons. It's my dream, but I hope so. Thank you.
Okay, thank you very much. And also there are several questions related to geopolymer and so on, but due to time limitation, maybe now Dr. Ekato please answer it by chat. So thank you very much. And then also I would like to show some question related to the durability of fly ash concrete. Someone asked how much surface life of concrete increase with fly ash addition, and also someone also asked fly ash concrete resistance to the chemical phosphotic and sheet and methanol and sulfate. And then that kind of point, probably Dr. Somnuk knows very well about the durability of fly ash concrete. Professor Somnuk, could you give some comment and answer?
Oh, that's a very wide question.
Sorry.
Very difficult to answer.
Benefit of fly ash concrete is something
very difficult to answer specifically. By the way, okay, in general, let me say in general. For example, in Thailand, we have already established one service life design standard. Of course, is considering the durabilities of the concrete using fly ash. I should say that if you have this kind of the performance-based design standard or specification, this kind of the durabilities or whatever can be taken care of by the standard. This is very general, of course, and I think it's item by item, right? Some properties fly ash is good for, but some fly ash may not be good for. So it's very general like this. Let me say like this, for example, when we talk about the chloride-induced steel corrosion, of course, fly ash is perfect, right? Even up to about 50% replacement or more than that, the concrete still behave very excellent. On the other hand, if you talk about carbonation, right, the more fly ash you use, of course, you will come up with a concrete which has a higher or larger carbonation depth. But regarding carbonation, we have to be very careful to evaluate the quality of the concrete regarding this carbonation, because if you use fly acid concrete, usually we evaluate those. Until now, we usually evaluate the carbonation resistance based on very short-term, right, test. But I believe that if you just keep monitoring the concrete using fly ash for a very long time, I think many of the countries found out that the carbonation resistance of the fly ash concrete is not so bad. It's not so bad. So maybe in the future, we may have to change a little bit of the idea, right, of the way of thinking. Of course, we are now facing the problem of the global warming, and carbonation actually can be something good, right, rather than bad. As long as you can, right, you can estimate and you can make sure that this carbonation will not make the steel inside your concrete getting corrosion too fast. And so this is why I try to emphasize on the performance-based design standard specification. No. You asked a very general question. I'm sorry, I have to answer in,
Thank
in
you,
such
thank
a
you,
very
thank you.
general.
Yeah, but you are very completely answered as I did.
Yeah, as it
expect.
also as it prior should be bad, should be good, should be good. Of course, depending on the type of fly ash, some high calcium and low calcium. I think Dr. Rangana already showed the slide comparing the performance of the high and low CO, whatever. Okay, so some of the properties high CO is better, some low CO is better, something like this. Okay, so I cannot answer clearly. I'm sorry. Yeah.
No, sorry. I'm sorry for asking the very difficult question, but you completely well answered as I expected. So, almost time for the break. Maybe I would like to have about 15 minutes break, and then I would like to start next session from the Thailand time to 50, Japan time for 16 for the 4 p.m. for 50. So, thank you for your kind joining the first session, and also I would like to would like you to join the next session also. Thank you. A short break. So now time to start the next session. Can you hear me? I would like to start next session. Next session, we will also have the presentation from the Indonesia, Thailand, Japan, and Indonesia. So firstly, I would like to invite the first speaker, Ms. Johan Swarnau from Indonesia. Could you please start your presentation and share the screen?
Okay, thank you.
Okay, we can see your slide. Okay, could you start?
Okay. Okay, thank you very much. Okay, good afternoon, everybody. So thank you for the challenge, the chance that given for me for presentation, for present my presentation. I am lucky today that to represent the concrete industry from Indonesia to share in this forum. Okay, I am from practitioner. So now I am a director from the PT Sebuah Indonesia. Is the ready mix and precast company from Indonesia. So Sebuah is national company in subsidiary of Sebuah Corporation. It group which has a large business in the earth region of Indonesia. So our city in Makassar. Now with our vision of becoming the best and largest ready mix and precast company in Eastern Indonesia, we will always provide the best product with excellent quality and service. And our commitment is to always innovate in developing high quality and environmentally friendly product, adhere to sustainability practice, and actively strive to reduce our impact on the environmental. So we have the two product. There is a concrete ready mix and precast. Okay. So my topic for this presentation is with the title is the fly ash and concrete production, improving performance and cost efficiency. The first, we use the fly ash for our concrete. That fly ash is a source from power plant Jeneponto in South Sulawesi in Indonesia. It's the Sulawesi Island. So the source of fly ash from the Jeneponto power plant with the capacity to time 125 megawatt that located in the Jeneponto Regency, South Sulawesi, Indonesia, with a distance about 82 kilometers from Makassar city, where our factory is located. And is the characteristic of fly ash. So based on the following fly ash sample characterization, they are from test data. There are several important mineral content in fly ash that indicated the type or class of fly ash. So from this characteristic of fly ash test, we can see that this class of flies is include the F class, because the total of the silicon dioxide and aluminum oxide and iron trioxide is more than 70%. So these classifiers that we use for our factory in Makassar. Okay, so we already use flyers is about 10 years ago. We start for the use flyers, these flyers from this factory. So if we talk about the benefit of flyers usage in concrete industry, there are three aspects we can see what the benefit of the flyers usage. The first is the technical aspect. So in technical aspect, the following are the benefit of flyers in concrete, both in the fresh concrete and hard concrete condition. On the fresh concrete condition is workability, decrease the bleeding, segregation, and low head hydration. In the hard concrete condition, it's about the strength and durability, permeability, corrosion resistant, and self-healing. And the second benefit is we can see from the economic aspect. So we get some following benefit. The first is we can reduce the cement cost. Cement is the largest component of the material cost of concrete production. So by utilizing by fly ash as a supplementary cementitious material, where the general condition that the price of fly ash is cheaper than the price of the cement. So greater the percentage of the fly ash, it means that the cheaper the cost of concrete material. And then we can reduce the aggregate cost. In addition to having chemical characteristic, fly ash and bottom ash also have a physical characteristic, where fly ash and bottom ash with further processing can replace coarse aggregate or fine aggregate in concrete or its derivating product like the precast, liquid brick, and others. And next, the low maintenance. Concrete produced by the fly ash will have the better durability. So for a long period of time, the maintenance of concrete is less. The repair of the damage that occurs can be minimized when we use the fly ash on the concrete. Next, about the transportation and logistic costs. This depend on the distance from the factory to cement plant, or the distance from the factory to the source of fly ash. It means the power plant. In general, there are more power plant in the city than cement factory. And the next is the waste disposal cost. In power plant, require a large amount of money to manage fly ash and bottom ash. If careless handling can result the disaster the surrounding environmental. Utilization of fly ash for concrete is simple, cheap, and safe. The cost to be paid by the power plant management can be reduced significantly if fly ash used to the concrete. Next aspect is the environmental sustainability. Fly ash use can reduce the carbon dioxide emission because the main component from concrete is the cement. And we know that the cement production is contribute about 6 until 7% of the total carbon dioxide emission into the atmosphere. So by reducing cement consumption, we help reduce the carbon dioxide emission. According to some data source, that the use of fly ash for concrete can reduce about 30% for carbon dioxide emission from the previous time. And next, the lower energy consumption. A reduction in cement consumption means that reduction in energy consumption as well. The third was reduction. Before the utilization of fly ash for supplementary cementitious material, fly ash waste that was not handled properly cause environmental damage problem and cause result in human disaster. So utilization for concrete will help in the reduction of unused waste from the power plant. And the fourth is the improve durability. It's about the service life. So by increasing the durability of concrete, it means that the service life of the concrete product is longer, so that the risk arising from construction activities that damage the environmental can be minimized too. So it's about the technical aspect. So we have some advantage with use the fly ash. The first is improve the workability. So it increase the as we can increase the slum result of fresh concrete. In our product, some concrete that use the high volume flash concrete, it's they behave to the self-compacting concrete. So the slope very high. So this can easy for the casting the concrete to the side. Second, decrease bleeding and segregation. So the physical characteristic of fly ash can improve the cohesiveness of fresh concrete. The third, increased lead compressive strength. So fly ash cause the low initial compressive strength in concrete up to 28 days. But after 28 days, the increase in the compressive strength continue until more than 120 days. The fourth, increase resistant to alkali silica reaction. Five, increase resistant to sulfate attack. So concrete with fly ash can anticipate condition in a coastal area where the influence of the seawater or sulfate attack can damage concrete performance. 6. Less heat generation during hydration. It's very helpful in mass pouring casting, where usually the thickness of the concrete is quite large. Yeah. Sometimes 1 or 1.5 meters. So in this condition, if there is a temperature difference, maybe also this can be problem because in concrete, when the hydration process is can increasing the temperature of concrete. 7 in increasing for refinement. And 8 decrease permeability. Fly ash particle size fill void resulting in increased concrete density. So with fly ash usage, we can increasing the density, so we can got the concrete with the higher density. But in practical, sometimes we meet the problem or disadvantage. Yes, the first is inconsistent characteristic and color the fly ash. The quality of fly ash is influenced by the quality of coal and the heating temperature at the power plant. Because it is waste, so it's very possible that characteristic of the fly ash will inconsistent. The color of fly ash also varies depending on the composition of the coal and the combustion process. Sometimes we meet the fly ash with the brown color, light gray, or dark gray. And the next disadvantage, sometimes our customer is unfamiliar with the fly ash color. Sometimes they complain about the color because the customer mindset that regarding that the color of the concrete is gray. So when customer meet the concrete with the brown color, they always just that the concrete is not good quality. So the third, the disadvantage is about the slower the strength gain. Because fly ash causes the slower strength, so that for early strength concrete requirement, material engineering must be carried out. For example, by adding the chemical admixture. In our factory, we use the type D of the admixture is the retarder, and we use the super plus, and sometimes we use the accelerator. So this advantage the inconsistently of fly ash quality. The key benefit of fly ash is decreased permeability at a low cost, but low quality fly ash can also improve the permeability. For increase the need for high conducting mix. And the sixth, high carbon fly ash material prefer to use more water. It's not recommended to use fly ash with a high carbon content with greater than 5%. In our current application now, we already use the fly ash with the percentage about 35 until 40%. So for the retail project, we always use the price content about 25 until 40%. Excepted if the project have the special requirement. And the second application is about the customs specification project. Last year, we have the project in our city with mass pouring about 2,300 cubic. The name of the project is Sudirman Street Tower. So the pouring must be finished on the maximum 36 hours with the grade FC 30 megapascal. And the request for the temperature maximum 32 degree Celsius. So in concrete, we use the fly ash about 15%. And for the minimize the temperature, we use the ice. So the temperature still under control is less than 32 degree Celsius. In the next application, now we have product the pre-stress pile that use the high volume fly ash concrete. So the pre-stress concrete, the grade is FC 45 megapascal, and it must be high early strength concrete because we need to release the steel cable before in the 24 hours. Pre-stress production is limited by strength and time. Pre-stress concrete must be able to reach curtain tensile strength so that the steel cable can be released. The time required for release affect the speed of the production. So when we use the fly ash about 50%, it causes the initial strength to be slow. So in this condition, we do the material engineering by adding the chemical mixer. So for this product, we use the Super Plus and accelerator because we have to reach the strength and 21 megapascal before the 24 hours. So next, I just want to share about our cost efficiency for using the fly ash. So at the first table, I try to compare the three grades of the concrete. The first is FC 20 megapascal. We compare with the no fly ash and fly ash with 40%. So with this comparison, we can see that at the FC 20, we can reduce about $5 per meter cubic for the concrete, or about the 13.9% from the total material cost. And for the FC 25, we can compare that we can saving the cost is 5.62 US dollar per meter cubic, or about 14.5% from the material cost. And then for FC30, if you compare between the non-fly-ash with fly-ash 40%, we can reduce the cost about 6.43 US dollar, or about 15.6% from cost material. And the second table, I will show the comparison on the high volume fly-ash concrete that we use for the precast sheet pile. So we can reduce about 8.5% of material costs in pre-stressed concrete FC45. So we can see the comparison. When we use the FC45 non-fly ash, the total of material cost is 56.5 US dollar. But for FC45 with fly ash 40%, total cost, material cost is 51.67 US dollar. So we can saving about 4.8 US dollar, or about 8.5% from total material cost. So what the next our planning for application of fly ash? In our planning, that no, we still research in our laboratorium that we want increasing the fly ash content in the concrete. So our target until the 80% of the fly ash. Next, we're planning for produce the railway sleeper with the high volume fly ash concrete. We know that not the application of the fly ash for rail sleeper has been maybe used in the Australia and Japan with the geopolymer product. So in Indonesia, where the influences of the marine environmental is very dominant, I think important for research the application of the high volume fly ash concrete for rail sleepers. So target in next year we can already produce this product, the railway sleeper high volume fly ash concrete. And the next is the cellular liquid concrete with fly ash. So we will try to use the fly ash for replace the cement, and we use the bottom ash too for replace the fine aggregate. So with this product, we hope that we got the more efficiency, we can more the saving cost for the material cost. Okay, so this with our summary that there are many opportunity for utilizing fly ash and bottom ash in Indonesia. Material engineering needs to be carried out so that quality requirement can be met. Proper handling of fly ash and bottom ash produce a concrete alternative with high performance, cheaper and environmental friendly. Okay, thank you. I think it's our presentation.
Thank you very much. That last one out. Okay, so let's move to the next presenter. Next presenter is from Thailand. Mr. Sakarin, Dapatkan channel. Would you please start your presentation? Okay, share.
First of all, I would like to give you a short brief about how the fly ash works to improve the concrete property. As you know, you can see here, the physical of fly ash itself is look like spherical. So it's very good for the concrete to improve the workability by the ball bearing effect. And it's really helpful for pumpability. A lot of projects in Thailand using the fly ash to improve the pumpability. The next one is about the durability, because the fly ash gives like a osmotic reaction and give more dense concrete in the future, the less strength. So this one is also very important for some kind of severe environment. The next one is the fly ash. When we use the fly ash in the concrete, you can reduce the water content in the concrete, so you can reduce the shrinkage. Talking about the drying shrinkage in the concrete, this is one thing that we always use for the floor type and the large area casting. It's really helpful for this. And the highlight today that I mentioned, you can replace the cement to reduce the heat of the concrete when you cast like a large volume or mass concrete. So this is the thing that fly ash can helpful. And also, recently we have research about the floor that require toweling on the floor, because after finished construction, this floor gonna face with like a wear resistant, something like that, because a lot of forklift will move on the surface. So toweling is very important for this kind of floor. And we found that fly ash can extend the finishability of window of finish when you towel. So that means you can finish quite a long time and you can make really flat floor. That is the effect of fly ash that we found right now. So this is overall the benefit of fly ash. I just want to give you some photo of application in Thailand that we use for various concrete applications. For the concrete type here, you can see we use for general one, cast the concrete structure, post tension, you can see the fly ash percent to replacement the cementitious material, and start from no fly ash until 30% of replacement to the cementitious material. For the post tension, as I mentioned, post tension in Thailand we use for the high-rise building. So we need some fly ash to give the better quality of the pumpability of the concrete. And the ball ply, we prepare fly ash around 30 to 40%. Even in the underwater concrete work. And if we talk about the durable concrete, as I mentioned, industrial floor, we use around 20 to 25%. For the sulfate resistant, we use around 30 to 40%. For the proof concrete as well, marine concrete, we use around 40 to 50%. For the special one, like high strength concrete, self-compacting concrete, and low heat concrete, that today I'm going to give you some information in detail. We use from 25% until 60%. This is commercial in Thailand right now, and you can see some project here. This is some project that we use fly ash for marine environment and also the sulfate environment. And as some Professor Smith mentioned, we have our own performance-based standard guideline for the design to for durable structure based with like a severe environment. So the benefit of fly ash, it can, for the chloride content, can resist the chloride very well. The chloride penetration is gonna low when you replace more fly ash with reduce the water cement ratio. This is some project that is in Thailand, and also the sulfate resistant as well. Some water treatment tank and some soil that have a sulfate condition. This is a benefit of fly ash for durability. Also, as I mentioned, for the floor, for the waterproof concrete, we found some effect from the fly ash when the concrete cracked and fed with the moist, some moist environment. After that, it can healing itself when the moist come to the structure. So it's the effect of fly ash as well. So this one just want to show you what application that we use. And for self-compacting, use a lot in Thailand right now. Some like a thin shell structure like this, difficult to cast by people, difficult to vibrate the concrete. We use a self-compacting concrete. Even the congested reinforcement, this one, I think it's close to the SIIT here and Thammasat University, the expressway at Chiang Mai. I think Professor Smith also involved this project for the cast self-compacting concrete. And so on, many structure that for repairing using the fly ash. This one is used around 40 to 50% to repair cement sheds. And used for high strength as well. I saw here for the vertical member and also the horizontal member like a slab. And we ever try to make the pump simulation for the concrete. You can see here the pump line. The distance of pump line here is about 600 meters. We pump the concrete in and we observe the concrete out with no any problem when we use the fly ash like this. So many applications in Thailand we use fly ash so far. Right now we general use for the C80 for the high strength concrete in Thailand. Okay, this is some background of application in Thailand for using fly ash. So this is the highlight one I would like to give you information. As I mentioned, we use the fly ash for low heat concrete structure, like a mat foundation. This is our past record in Thailand that we have ever produced a concrete using high volume fly ash. You can see here since 2014 to 2020. This is the mat foundation that we use so far, high volume fly ash and continuously pouring in one time. First one is the volume is around 8,000 cubic meter with the strength here. We repair the fly ash around 50%. Get the number of temperature here and the thickness of structure, you can see the first one is man-president is around 3.4 meter. And the next one, more challenge, but the strength is not higher. It's equal, almost the same. So, sorry, this one is in KSC, around 28 MPa. And the volume of concrete become higher, 12,000 cubic meter, continuous pouring, but the strength is not high. So it's not an issue much, but we use fly ash around 60% to replace the cementitious material. And the interesting thing for this project is the thickness is quite high, 8.75 meter. This is quite high thickness of the mat foundation that we ever produced. But it's not like a big area, just only in the core of the foundation. The last one that I would like to talk today, the mat foundation of One Bangkok project. This one is very special because the specified strength is C60 MPa. You can imagine that very high strength, and the thickness is around 6 meter. So when I heard that this project gonna come up and start, it's quite we are quite worried about the concrete, how because the owner and the contractor, they would like to cast concrete in one time, because otherwise you need a lot of days to cast the concrete, you need a lot of rebar, and you need a lot of shaking to transfer to split casting. You got a lot of work to do. So within one time, we already done that, but I will give you information later on. And we use the number 60% of fly ash for this project. So before I'm going deep down in the detail, I would like to give you the background of the project. This is a project called the One Bangkok. It's quite very much very popular now in Thailand. Placed in the city center of Bangkok, and you can see here the number of buildings, around 70. The project is kind of mixed-use and a complex project. So you can see the consultant, number of consultants here, and there are many contractors, many contracts in this kind of project. This is a very big one from our experience in Thailand. And you can see here a lot of mat foundations that cast the concrete. But today the highlight one is here, O4H4, this one. This is if we cast concrete in one time and we can finish that, we can achieve that, it's gonna break the record that we cast the largest cast in Southeast Asia so far. So this one requires, as I mentioned, C60, and we have to think about the low heat property of the concrete. So I will give you more detail. Before doing that, when we start the meeting from all parties before the project begin, for the mass concrete and kind of mat foundation like this, we have to concern two items. Yeah, the first one is a differential temperature of the structure here. In general, in the core of the concrete, it's gonna give a high temperature at the limb of the structure, and the edge of structure can give temperature. So if if there is differential temperature, we have chance to move the concrete, shrink and expand. Different expansion, that means have potential to crack. That is a thermal crack. We have to concern about this because we have to put some rebar to control the crack around this area. And another thing is we have to concern is about the peak temperature. For this project, we talk a lot about what is the number that we should do for the peak temperature. Otherwise, if we don't consider this, we're going to get like we call it EEF in the future. So we try to get literature, and we try to sit together and figure out what the number that we should do. And some recommendation they provide that if you use fly ash in the concrete, you can maximize the temperature to be limited around 85 degrees Celsius. So we talk about this number for this project. And this one is a table that summarizes what we talk about the concrete property for the project. First of all, as I mentioned, we talk about 360 for the mat foundation, but in general, we have to use high volume fly ash. So that means we cannot, in general, we guarantee the composite strength around 28 days. But for this one, to achieve 360 at 28 days, I think it's impossible. So we talk about 91 days guarantee the strength from the concrete supplier. This one, it doesn't matter for the construction sequence because the concrete can develop the strength. Once 28 days, it's around 60%. So many workers can continue their job. It's not any effect from this. So this one is a number that we talk. And we would like to have like a high workability concrete because we cast a lot of, you can imagine that 28,000 cubic meter, we need high workability concrete and long working time. It's around 4 hours. And the setting time we set around 12 to 14 hours. The maximum temp, as I mentioned, 85. And the fresh concrete temperature, we control around 35 degrees Celsius. The max temp different on that time, we talk about 30 degrees Celsius in general, but in detail, we have model from Professor Somnik and SIT to calculate the steel rebar to confirm that the crack can control. And the crack control for this project is around 0.4 millimeter acceptable because after this, they're going to do like a waterproof treatment at the structure after this. And we need low bleeding concrete. And because after they cast the foundation, they will travel on the surface to make like a car park area. So they don't need to do like a topping again. This is a thing that we working. And you can see here, we developed the concrete for this one. We use 60% PFA or fly ash to replace the cementitious material. The cementitious material for this one is around 500 kilogram per cubic meter. And this is how concrete look like. And you can see here the slab retention at 4 hours. And this is our lab test after we do, you can have a look at this. And we get the strength around 56 there, 70 MPa. This one is in cube, but we can convert around 65 something around this. This is our lab, and we try to shrink it as well. And we select the proper admixture to be used for the project. And this one, rather than only the concrete material itself, we have to think about, because the structural design, they design the steel bar to for the structural point of view. But this one, we closely working with the SIT and Professor Somnik to give the model to simulate the structure of the mass foundation for this one, because it's the new one. Everyone concerned about the structure, about the thermal crack, because it's very high depth and also very high strength. So this one, I got information from Professor Somnik. He has a lot of model, and the model is quite excellent. It covers all aspects. Since you have the total heat generation from different kind of material, have the temperature of concrete prediction, you have the heat conductivity, heat transfer coefficient, combine all together, and even the environmental factor. We have all aspects together to combine as a model, and after that, we calculate the structure. What is the tensile strain that's going to happen at the structure? After that, we put the rebar to control the crack. This is the overall quite very excellent work from SIAT. And as I mentioned, in Thailand, we use OPC cement as general. So for this project, we would like to use OPC as well for this one. Before we casting, we try to simulate the model. And this one is the shape of the foundation look like. And we get the peak temp is around 83.5 degrees Celsius. So on that time, we talk to the owner, we talk to the consult, but the owner and consult said that it's too risky. We have only 1.5 degrees Celsius to spare. So this number is quite high from model from Professor Somnik and SIAT. So that we change our mind to change the cement type. More than we use the fly ash 60%, we use the moderate with cement to combine with the fly ash 60% as well. So after that, we calculate the model again. We get the peak temp around 81 degrees Celsius. This is a thing that owner become more happy about this because the number is reduced. And after that, we prelim the model. And this one, the SIT and the team contact deep down, analyze in detail of the structure, and they get the peak temp around 81, something like that I mentioned. And we got that some area we need to put more rebar to control the crack, particularly at the edge of the structure. This is some animation and some photo that analysis from the SIT model. And even the models, after that we change the cement use. So we try to understand and we try to make sure that cement, when we change the cement type, it's gonna work well alongside the model. So we did some adiabatic test in large scale, compare between OPC cement, ordinary Poland cement, and the moderate heat cement, and we get that number of the temperature reduction around 3 degrees Celsius. And after that, we quite happy about this one. And after that, we move to the plant scale. We count like a 1 cubic meter and compare the temperature peak and again. So we get the number again, 3 degrees Celsius is quite close to our lab test. So everyone happy for this one. So we go on and we cast the concrete. You can see the number of truck here, a lot of truck, and we have pump alongside the truck. And as I mentioned, after they cast, they finish concrete. And this one is the concrete look like and the strength development of the concrete that we got. So it's quite happy for our issue. And after that, we put the thermocouple to monitor the temperature at each point. And you can see here, we get the number here around 81.1. 81. We compare. You can see here the specified temperature max here, and this is the red line is the middle temperature that we measure from the real structure. And you can see maximum is around 81.1, and we predict around 81 from SIAT. And also we have our software to compare with the maximum temperature as well. So the prediction and the actual is quite close. So that's where everyone happy about this number. And the differential temperature you can see here, it's not much. It's around 18 degrees Celsius, something like that. The summary. So we have cast and we have achieved for H4 for the mat foundation with 60 MPa. And you can see the volume here, the number of plants that supply of the concrete, number of truck, number of chute. We spend around 36.5 hours casting continuously. And the max rate of supply is around 1,400 5 cubic meter per hour, and average around 1,000, something like that. So it's our pride project here. And this is after we observe, after casting, we found some actual crack, but it's very few. So it's acceptable for our party. Okay, before I end, I just have some video, just short video to show you our project. Yeah, just you can imagine what the concrete when we cast at the top side look like. Skip some with some overview when we cast concrete. You can see the number of trucks and you can see the platform. This is the main contractor that we get together casting. Okay, you can see the concrete pumping, shooting together, and there are some board showing at the real time that how many concrete have been casted. Okay, this is the area. You can imagine it's quite big area in the center of Thailand. And the challenge one, as I mentioned, is 360, never done before for the MAC foundation. A lot of people, it's not only the concrete material, it's about the supply concrete as well, and the planning, how to place the concrete at the position. Okay, this is actually it's not the highest one, but it's the previous one. The next one is higher, but we didn't make a video, but I already gave you presentation. So that is my presentation today. I hope you enjoy this. Thank you.
Thank you very much. Okay, let's move to the next presentation. Next presenter is Dr. Toichi already presented, so Dr. Yamamoto. Now, okay. Could you share screen? Stop your sharing. Okay.
I'm sorry for messing up this meeting program. I will introduce you about the rapid assessment method for programming activity of Flash. I named it as API method. And this will be in the next revised version of Japan Industrial Standard A6201. And background of this API method is like this. The physical chemical properties of flash have changed due to the diversification of fuel cores. In Japan, we imported much amount of coal from the many countries. So the character of the flash can be easily changed. And next one, we need to have some rapid estimation method for obtain the properties, especially for the strength development about the fly ash. Now we apply the model test, then it takes about 1 and 3 months to obtain the result. So we need to shorten the testing period. And the objectives of this research I show you today is firstly optimization of API method test condition to improve the accuracy of rapid estimation of activity index. Activity index is derived from the motor test. And secondly, a purpose of quality determination method using the API method. It's a goal of the Japan industry standard. And there is already there are a few testing methods. Firstly, it's named the Platini polygonality test. It also uses cement suspensions, and the suspension is made from the 20 gram of powder samples, and 20% is polygonal material like fly ash, and the other 80% is cement. And the reacting condition is like this: 40 centigrade, and keeping it for 15 days. And second one is like this, using the calcium hydroxide, and we mixed 20 grams of the samples, and in that 70% is polygon like fly ash, and other 30% is calcium hydroxide. And there's need to cure about 28 days and 91 days for the paste specimens. And after that, we determine the content, consumption amount of calcium hydroxide by TGTTA, like so. And third one is like this Chapel test modified. In this case, it was used in France. I remember that. And they use metacoloring in the concrete admixtures. And this is not fresh. Metacoloring is have much high reactivity than the fresh. And in that case, they mix 1 gram of metacoloring and quick lime, meaning CaO, like a free lime, 2 grams, and mix it into the 250 milliliters of pure water. And the reacting condition is 85 centigrades, and for keeping it for 16 hours. And we need to estimate about the consumption rate of the calcium ion. By the way, my testing method, API method, the testing procedure is like this. Use plastic container, like it's a very small one, and the amount of sample is 2 grams of fresh samples and 2.4 grams of cement. We use the ordinary type one, and mix it with 80 milliliters of water, a purified one. And the reaction condition is like this, 80 centigrade, and keep it for 28 hours. This one is for the estimation of the fresh activity. And in parallel, we need to set like a control specimen. It does not contain flash, but only the OPC case. 2.4 grams of OPC and mix it with 80 milliliters of water. And we must keep it in the thermostatic water shaker bath, like shown in this picture. And after that, 28 hours of the curing, we take out the sample bottles and quench in the ice water. We need to cool down quickly. And after that, by using like the pictures, using syringe filters, and we must have a filtration. And after that, we need to dilute it in the suitable condition for each equipment, like ICP. I'll show you that small movie like this. We shake it in the 80 degrees of hot water for 28 hours. After that, we got the data firstly for the difference. We must obtain the concentration of calcium in the reference data, meaning obtained from the OPC system. And secondly, we must get data, evaluation data from the cement and flash mix system. It's like CA, F plus C. And after that, we calculate very simply API equal like this. We obtain the data to estimate the consumption rate of the calcium ion from each solution. And small I means the repeat number. We must repeat 3 times and obtain the version index like API. In this research, we use 8 samples of flash named A1 to F like this. And they are all the type F flash because we use only type F flash in Japan. The silica content is from about 55% to up to 66%. And calcium content is very low. It's a thicker type of the flash. And table 2 shows the glass ratio, glass amount of glass in the flash. It's noted at the vitrification rate. The amount of glass is from 72 to 85% also. And also I show you about the basicity. Basicity, it's amount of calcium and magnesium and aluminum to silica ratio. The basicity is from 0.27 to about 0.5 also. There's much difference amount of these samples. And firstly, I show you about the test result. And this shows the impact on the API value from the type of the difference of the cement. We applied 3 cement, and it's named cement 1, 2, 3. And the vertical axis shows the API, and the horizontal one shows the sample number from A1 to F. The reactivity shows much differences among those. But the differences between the cement type is very, very small. So I think the difference of cement have less impact on the value of the API. The next figure shows the result about the relationship between API and motor activity index. And the left figure shows the result from using the cement 1, and right one shows the result from using the cement 2. As shown last figure, there is no difference between the results obtained from using cement 1 and cement 2. But the vertical axis like this, the activity index shows a little bit differences between those two cement. So I think the type of cement mean difference of the lot of the cement have a little bit big impact on the result of the motor test, mean motor activity index. So I think it is a little bit of a problem for the estimation of the activity of the players. And next figure shows the result from the data. We operated a round-robin test with 5 institutions. I delivered 3 mesh samples that name A1, B, and E. And the upper row shows the CAC, means the concentration of calcium ion in the standard specimen, standard line. From this data, all institutions have also the same result. And next slide shows the API. Each A1, B, E shows almost the same. But I noted in the SD, it's a standard deviation. I want to estimate the repeatability of the test. So I noted the number. I also estimate coefficient of variation. I estimate this. And in case of institution 3 with using B, the standard deviation value shows 4.34. And the value in the coefficient of variation was about 5.6. So I decided to note in the Japan Industry Standard if after we conduct the API test with repeating 3 times, and if the coefficient of variation exceed 6.0%, you must conduct the test again from the sample weighing. And last one, we must decide to how to use the result of the API for the estimation of the activity index of the bias. The horizontal vertical axis shows the 28 data from the motor activity index. In Japan standard, in JIS, there's 4 types of the class from 1 to 4. The lower limit for the type 1 is very high reactivity bias. The low limit is now 90%. And for type 2 and type 3 is lower limit is now 80%. And last one, type 4, we must determined the lower level as 60% now. And by the way, for the vertical axis, there's a linear relations like those plot. And for type 1, under limit was determined as 80% in API. And for type 2 and type 3, we determined the lower limit for 60%. And for type 4, we determined the lower limit for 45% as this. And next figure shows the result, the relation between API and 91 days motor activity index. There's also linear relation between those values, and the results show like plot. And the API and the limitation, lower limitation of the activity index is shown like this. And in motor activity, for type 1, the lower limitation was 100%, and for type 2 and type 3, the lower limitation is 90%, and type 4 shows the lower limitation as 70%. And to see the horizontal axis, we determined for the type 1, the lower limit is 80, and for type 2 and type 3, the lower limit is 60%, and for type 4, the lower limitation is 40%. As shown in those figures, we only need to operate API method for one time. So we can determine only one API, and we can determine those both motor activity index, 28 days and 91 days data. It's very simple. This figure shows my interpretation during those last two figures. So I will skip this figure. And I show you the summary. Based on the experience gained from many years of research at RIPI and the results of the round-robin tests conducted by producers and users, it was clarified that the potongan activity of bias can be appropriately evaluated by API method as well as the activity index by the motor test. And it is proposed to newly in GSA 6201. The criteria for judging potongan activity of bias for concrete according to API method are as follows. For type 1, the lower limit is 80%. For type 2, the lower limit is 60%, and also that in type 3. And for type 4, the lower limitation is set as 45%. It's all my presentation. Thank you.
Thank you, Dr. Yamamoto. Okay, so I'd like to move to the final presentator from Indonesia, Dr. Ivan Sandi Dharma. Could you share your screen and start your presentation?
Okay, thank you very much. Good afternoon, everyone. This is my presentation. I hope my presentation can keep you stay on the seminar. The title is a microstructure of slag and fly ash blended in cement concrete. My name is Ivan Sandi Dharma from Institut Teknologi Bandung in Indonesia. Okay, the background. First, the need to explore up to the microstructure level. Of course, when you use when you add another cementitious material in the mixed proportion, at least maybe at least you have to explore or analyze not only for mechanical properties but also in microstructure level. And then from microstructure level, microstructure, we can also explore the durability things from viewpoint of pore structure. And then in here, in my presentation, of course, I will try to introduce a cutting-edge technology by using computed tomography and combined with several methods and final new finding in order to contribute to the current understanding. Okay, as you can see here, cement-based material representative multi-phase heterogeneous material that are strongly affected by characteristic of each constituent. Therefore, we need to understanding the microstructural characteristic. Up to now, we apply MIP, micro intrusion porosimetry, X-ray diffraction, as mentioned by Januarti Senpai. Next, SEM, scanning electron microscopy, can be combined with BSA, backscatter electron, and then transmission electron microscopy, or TEM, nuclear magnetic resonance, or NMR, and the final X-ray compute tomography. And then for MIP, one of the most widely used technique for determining the pore size, but the drawback, as we know, we have a bottleneck effect and also the damage on the specimen during the pressure loading. For XRD, the drawbacks, XRD is non-destructive analytic technique, but it's only reliable when you investigating crystalline compound. For SEM, we know only 2 dimension. NMR is quite difficult to investigating the spatial characteristic. But for X-ray, up to now, still there is no reporting regarding the shortcoming of this method. For in this presentation, I will try to explore to share to you 2 type of X-ray-CT here. First, microfocus X-ray-CT, and then the second one, synchrotron X-ray-CT. Microfocus X-ray-CT here, I used 2 types. First in Hokkaido University, and the second in Bandung Institute of Technology. For X-ray, for synchrotron X-ray-CT, we use synchrotron X-ray-CT in Japan. The difference between microfocus X-ray-CT and synchrotron X-ray-CT, especially in the focal size. In the microfocus X-ray-CT, the minimum of focal up to now maybe around 10 micrometer, but for synchrotron, we could achieve 0.5 micro. So the level of very, very small size of the microstructure can be achieved by synchrotron X-ray-CT. But again, the drawback, maybe I can say the drawback, if you try to achieve smaller size of voxel, you have to prepare smaller sample, and then it's for a synchrotron X-ray-CT usually used in cement-based phase. But for microfocus X-ray-CT, of course, is quite high compared to the synchrotron X-ray-CT. In our recent research, we could achieve around 15 to 20 micrometer size. And then the specimen could be in cement paste, mortar, and maybe concrete. But again, here in X-ray-CT, not only the image, we could achieve many things. In X-ray-CT, beside the image itself, we have a CT value. And then for X-ray-CT, synchrotron X-ray-CT, we have a LAC, linear attenuation coefficient. Both of CT and LAC, we could make a good relationship between the CT or LAC to the phase of a microstructure itself. Here, as I explained before, LAC provided by synchrotron X-ray-CT allow us to identify different phase in cementitious material. It's very easy compared to XRD. And then CT number produced by microfocus X-ray-CT allow us to detect the change in the density in the cementation material. So by using micro focus eccentricity, we could find the difference. For example, before and after leaching test, before and after carbonation test, and before and after high temperature exposure. In here, I try to explore the use of eccentricity in a four type of topic. First, microstructure itself, and then pore structure, crack geometry, absorptivity, and diffusivity. For phase analysis or microstructure, here we use synchrotron eccentricity in Japan. We use cement paste specimen in the cement paste level. We use OPC and low alkali cement. In low alkali cement, we use high volume of fly ash. This in here, water to binding ratio 0.5, and then we cure the specimen from 2 up to 1 for 6 days. And then for the fly ash, we use type 2 GIS fly ash. And here I show you this is the image. One slide from the eccentricity. We have a bunch of slides. If I'm not mistaken, it's around 2,000 slides, similar to the bread. If you cut the bread, you will have the slice, and then if you try to immerse the slice, and then you have a 3D, similar to this one. This is a 2 day, and then 7 days, 28 days, and 146 days. This is from similar specimen, but different sample. And then in here, you can choose ROI. What is ROI? ROI is a region of interest, the specific area you choose to evaluate. And then from the ROI, you collect the ROI, and then you create a new specimen, and then you will achieve a VOI, volume of void. And then you can imagine in VOI you will have several slices, and then you immerse, and then you will achieve a VOI here. From here, here you can see here the brighter the brighter things in the image show the high density, and then the darker shows the void. Maybe quite similar to the void. And then from this VOI you will have a histogram. From the histogram, and then you can convert into LAC, linear attenuation coefficient. From the study, we will have the correlation between the LAC and specific items in the microstructure. For the example, CHS type 1 here, we use 15 kilo electron volt. The value of LAC around 23.43 LAC. And then from here, we could check the change in the microstructure during the curing period. As you can see here, we will have two peaks. First, the higher, and then the second is the lower. And then when you try to relate to this LAC value, you will find what is the growth. The growth of for example, CH, increasing in CH, reduction in CH, and then different type of CHS. In here, we can find the two type in this research. We found two type of CHH, type 1 and also type 2, based on LAC. And also you can see here the change in the volume of Fox cell for the CH for the CH in OPC sample, and also in fly ash sample. In OPC, by that time we will have an increasing in CH, but for fly ash sample we will have decreasing in CH. It could be better. I think it's more easy to use, and then to explore, and then to evaluate compared to the XRD. And then the second, as several presenters says that by using the SAM, you can find the fly ash particle. In X-ray CT, you can differentiate several types of fly ash. Here, we found a lower density of fly ash, and then high density of fly ash. And the final, we will have a cenosphere, high density in the outer, and then void in the inner. Now, later on, the void in the inner cenosphere, we call it cenosphere. There are cenosphere as well as plerosphere in the fly ash. This cenosphere may contribute to high porosity in fly ash sample. And then for a pore structure using the same specimen, same BOI, I have a histogram here, and then I try to thresholding to separate between solid and void item. And then here, as you can see here, the red one means void, and then the gray up to the white means solid. As you can see here, first, of course, in maybe in 2, 1, or 1 up to 3, we will have a very high porosity in both specimen, both OPC or also for fly ash. And then here, we try to evaluate more detail. Here we will have a percolated porosity, and the last one is isolated porosity. Percolated means connect from we can say 4 surface, from the left to the right, from the top to the bottom, and then also from the side to side. That's the meaning of the percolated. Isolated is isolated. It's not connect from one to another. And then here you can see the histogram shows the porosity versus curing period. As you can see here, of course, for OPC, we will have a lower porosity compared to the fly ash specimen. But again, as you can see here, by the increase in the curing period, as you can see, reduction in percolated porosity is more higher than the OPC one. Here, the contribution, as you can see here, as I mentioned before, we will have a cenosphere particle here. The presence of fly ash particle in the form of cenosphere, which has low density phase or void surrounded by high density of thin shell, contribute to the amount of porosity in fly ash specimen. So maybe this is the answer why in some research we found that for a fly ash specimen has the higher porosity compared to the OPC specimen. Maybe this is the answer. We will have you will have the cenosphere things, and then contribute to the porosity. And then this fly ash particle may not react during the curing period and remain in its original form at any time and might be calculated as isolated porosity during the pore segmentation and cluster multiple labeling process. And then for the crack geometry, again here we prepare 2 types of specimen. Again, one for conventional, OPC, and then second one using the fly ash. 2 types of crack. First, generated by flexural load, and the last one we generate by splitting tensile load. And then here for the flexural test, for the flexural specimen, we apply oven dry treatment, and then for a splitting test, we apply saturated condition. The specimen was immersed in water for at least 24 hours before diffusion test. So in this case, we will have absorptivity things, and the last one we will have the diffusivity things. As you can see here, this is the crack geometry. We have a 3 sample. First, OPC with lower crack opening width. Here we have 50.1 millimeter, 50.1 micrometer. Here, the second one, OPC with 152 micrometer. And the last, we have a fly ash specimen with 127. This is the image from 5 millimeter, 7 millimeter, 9 millimeter, and 13 millimeter from bottom to the top. And then after thresholding, we will have a crack geometry here. We will have a 3D of the crack. In here, as you can see, we evaluate tortuosity, I mean the straightness level, and the final constrictivity. Constrictivity means the variation of white crack, the crack white variation. Here, as you can see here, for all specimen, the crack geometry similar, around 1.2. Tortuosity, straightness of the tortuosity, value 1 means straight. If higher than 1 means you have some tortuous. And then post-constructivity, value 1 mean uniform in crack width, but lower than 1 mean you have a variation in crack width. And then this is the crack width distribution. We also calculate the crack width distribution using image, especially for bone J. Here you can, as you can see here, for OPC, as you can see here, for OPC, the distribution of crack is quite wide compared to the OPC. It's quite range from says 0 to 484. For the OPC, for the fly ash, from 0 to only 200. So as you can see here, part of the crack in the specimen in OPC were formed in the pore cluster, while some part are around the aggregate. Considering that the pore are connected to the crack width formed in the pore region was generally larger relative to the crack width along the crack length. Such condition can obviously lower the degree of crack with uniformity, resulting to the increasing in variation of crack width along the crack length. And for flexural specimen, also we calculate, we clustering, and then we will have a crack 3D in 3D dimension. As you can see here, the tortuosity is quite low compared to the splitting. So in here we can summarize for flexural crack, resulting lower tortuosity compared to the splitting specimen, and also constrictivity quite high compared to the splitting test. And for diffusivity test, as I said before, this is before we conducted the diffusivity test, all the specimen was immersed in the water for at least 24 hours. And then we conducted the diffusivity test. You can imagine, we put here, as I should mention before further explanation, the white wine here, we use a tracer. So the X-ray CT itself can be combined for the diffusivity test, for the mechanical property test, for everything. It can be combined. In here, we combine 3D imaging with the diffusivity test along with the time. As you can see here, initial 1 hour, 3 hours, 9 hours, and 24 hours. Okay, and also you can see here the penetration of tracer. Here, the tracer we use is cesium carbonate, non-radioactive cesium. We use this one because the higher level of density similar to the metal, so it contribute to the higher difference in the intensity of color. Here, as you can see here, crack fill with the tracer first by the time, and also the tracer also penetrate to the uncracked specimen, not only in the crack but also the uncracked matrix. Okay, this is thresholding. The observation of cross-sectional image of splitting tensile crack specimen in the cesium exposed to the condition shows that the tracer only fill the crack occupied with water. Thus, the immersion process for 24 hours before cesium tracer diffusion test, unfortunately, did not produce fully saturated crack and leaving behind the air pocket. In the next exposure track, the results showed that there is no additional crack space filled by the tracer. In this way, the diffusion tracers only follow by the path that formed on the short period of exposure time. And for the next, we also calculate the diffusivity along the crack. As you can see here, for OPC and fly ash specimen, resulting almost similar diffusion coefficient. So we can conclude the diffusion coefficient along the crack for every specimen is almost the same. It depends on the liquid itself. So here the diffusion coefficient along the crack independent to the specimen, independent to the either you use fly ash, either you use slag, or you use only OPC. And then for the last, here in my presentation, absorptivity test. This is from a flexural tensile, the crack was generated by flexural load. And then as you can see here, for the OPC, the crack, the tracer spread out into the specimen, not only in the crack, but also the uncracked matrix. But for the fly ash, as you can see, smaller spread compared to the OPC. Here, we can conclude that in addition, reduction diffusion coefficient for uncracked matrix in fly ash specimen could be related to the lower diffusion coefficient along the crack. And then drying for the addition, drying process before penetration test enhance the pozzolanic reaction, resulting in an increasing resistance to diffusivity due to the dense microstructure of fly ash specimen. And then, as a conclusion, I might skip this one, but the most important thing here, it is highly expected that by using X-ray-CT, the microstructure in cementitious material will be more explored in the near future. X-ray-CT again can be combined with another testing. You can combine with for diffusivity, permeability. You may check the change in the crack due to high temperature exposure and recuring, and then you may apply any condition. And the final, using the X-ray-CT things coupled with in situ tracer diffusion test would allow further understanding the transport mechanism of the diffusion in the crack cementitious material. And then for the bonus, recently we also conduct another test, not only using the fly ash, but now we use SAP, super absorbent polymer. Okay, and then for the last, this is okay. Oh, wait a minute. Hey. Okay, for the last will be presented by my students. Okay.
Okay, thank you for the chance. Let me introduce myself again. I'm Abdurrahman Yusuf from Master Candidate in Bandung Institute of Technology. I will present an effect of superabsorbent polymer utilization in cement-based material using X-ray micro-CT. Superabsorbent polymer is a polymer that able to absorb water until 200 times its weight. First, superabsorbent polymer used for pampers and farmland. In soak condition, superabsorbent polymer potentially used as internal curing medium. In this illustrate, superabsorbent polymer will release the water that initially absorbed. Superabsorbent polymer research massively in the last 3 years. For mechanical properties of specimen, compressive strength test is carried out at 1, 3, 7, and 28 days. In day 1, delayed hydration occur, which can be attributed to the retention of water in SAP. However, starting from day 3, the compressive strength of SAP specimen surpass non-specimen. This increment can be attributed to internal curing from SAP, which evidenced by failure area of the specimen. The crash surface for non-specimen was in the shape of lake that resembled of cement powder. Meanwhile, SAP specimen revealed a typical surface of hardened concrete. However, this study observed a 17% enhancement and overcome at early age in compressive strength for SAP specimen, while keeping key variables such as water content, water to cement ratio, workability, and compaction consistent. Additionally, this study uncovered the phenomena of delayed hydration at day 1 to day 3, as evident by the compressive strength between days 1 and 3, which yet to be explored in previous study. Porosity of specimen can be obtained from X-ray microsity from 3D image. Volume of interest of 1000 voxel chosen on core structure and can be obtained from thresholding. Porosity of SAP in 28 days slightly higher, but have some dominantly isolated, so superabsorbent polymer can be assumed not significantly influenced. Through two-dimension pore evolution, we can tell that pore isolated through the time. From X-ray CT, we can quantify pore in 3 dimensions. In non-specimens, significant change occur in day 1 to day 3, but in SAP specimen, significant change occur in day 3 to day 7. This indicate the delay hydration from some water still inside of superabsorbent polymer. We can also observe sphericity of specimen. SAP cause for more elongated following the SAP structure. To observe the durability, capillary absorption through crack will test it. So the SAP will split it and capillary suction using an potassium iodide as tracer for 24 hours. Therefore, we can observe the penetration of tracer. Non-specimen penetrate almost 4 mm and SAP specimen just around 1.5 mm. This densification capillary or gel pores confirm SAP as internal curing medium and makes more uniform hydration. Through X-ray CT, we can also observe crack geometry properties like distribution and constructivity. The distribution similar, but maximum thickness of from SAP specimen attribute to pre-soak SAP that bigger when absorb some water. And from 3 dimension of crack space, constructivity can be quantified. SAP specimen have constructivity value closer to 1 than non-specimen, because form uniform hydration makes more uniform crack width. To prove the presence of SAP, we can scan specimen with SAP that absorb some tracer. So SAP will be able to identify. From line profile, SAP showed in the center of pore. SAP evolution also can be observed. The SAP will be smaller because of the release process. For summary, we can say superabsorbent polymer effective as internal curing medium based on compressive strength and pore properties. Thank you.
Okay, that's our presentation. So for the conclusion, you can imagine that the use of fly ash can be combined with superabsorbent polymer as the internal curing, and then all of them can be explored or can be studied by the using of microcity X-ray CT, microcity X-ray microfocus X-ray CT. Thank you very much.
Thank you very much, Dr. Nagma, and also your student. And then now Q&A session, but almost no time for the Q&A session time. And also there are many questions in the Q&A, but Mr. Sakari kindly answered most of the question by chat. So I appreciate for your work. And then also someone asked some question, but someone asked how to measure the stress in concrete. then I don't know. He asked Dr. Dharma how to do it, but stress it would be difficult. Maybe you may chat something later. And then some question. Yes, some question I would like to summarize. Most of participants seem to be interested in some application of fly ash inside. And then Mr. Sakarin also answered most of the question. But anyway, Thailand has very long application of fly ash, and then they know how fly ash concrete is durable, and also some problem once something happen. And then probably most of participants interested in the fly ash application in future. And then Thailand one successful country owing to Professor Somnek and also other Thailand colleagues. So probably you may also differ. Professor Somnek published a lot of paper, CBM and CCC, and also RUANGGURU now producing a lot of paper for the any chemical resistance and something. I think so it could be something very useful for your reference. Also, someone very interested in geopolymer, as today's Dr. Eka Puttori did, and then she also published a paper, and then you can check her name in Google Scholar, and then you can also refer the paper. And then also geopolymer, also many papers published, construction building material and other international journal. I think that would be something interesting for you. And then from Japan side, we also now try to apply the fly ash, especially our case. Of course, Dr. Toichiga introduced the fly ash application for dam, but also we try to apply fly ash to prevent ASR. Because Japan, we have many reactive aggregates, then fly ash is one very good material to inhibit ASR. So Japan Railway company also applied the fly ash to prevent ASR. So if you have this kind of problem, probably fly ash also very useful. And then, okay, so then also I would like to finalize, but also finally I would like to give one big issue in future. So now probably most of you understand very big discussion on CO2 emission. Then now we also have the big discussion in Japan, especially industrial field, as well as academic. And then recently I went to the Europe, and also they always discuss how we reduce the CO2. If so, they always say, okay, we should not use the cement. And also then try to use mineral admixture. However, also fly ash is from the higher coal plant. So now with Japan also we a big discussion how we consider such kind of CO2 emission from the coal power plant. So I'm not sure how coal plant will be used in future. And then we may also need to find out alternative good material rather than fly ash in future. But currently, I already discussed with Professor Somnek. He said currently one good solution is like application of fly ash. But the near future probably we also need to consider something such kind of new material. Okay. So I'm very appreciate for all presenters and also all participants to have the very active discussion. And then finally, I would like to ask Professor Somnek Tangtemsiriku to give the concluding remarks. Professor Somnek, could you please give us the concluding remarks?
Okay, thank you. I will make it short. Yes, first of all, on behalf of SIIT, and I would like to also say that on behalf of the Engineering Institute Thailand, I would like to thank JSCE and AKI, of course, including EIT, to allow SIIT to host this seminar. I think that the information today to the researchers, maybe you enjoy some kind of the information exchange. For those students, you may learn something from the seminar. And I hope that this sort of the activities will keep on in the future, but maybe with different topics. No, it can be anywhere because during these days, you may not need to just go to come together, but we can do this kind of thing online. And I hope that maybe JSCE and some other countries, professional organization or academic organization can try to do more and more this kind of seminar in the future with different topics. And with this, I would like to end this seminar and hope to see most of all of you in the future in some other events. Yes, thank you very much.
Thank you very much, Professor Song. Finally, JSC side, do you have any some comment or from the organizing committee side, any information? Maybe you may say the video.
Nagai can say, sorry, I forgot to thanks to all of the speakers today. Sorry. Thanks to all speakers also and participants.
Okay, thank you. Yeah. Okay, so I would like to close, but the JC side, there any information? No?
Sorry.
yes,
So,
Ron.
Asamu Sensei, sorry, that is probably the link for the certificate of attendance. So we have already shared it for several times in the chart, but if any attendant want to have it, please see in the chart, we have the link. So if you fill in that one, so we will send you the certificate of the attendance later.
Okay, thank you. So, so finally, we would like to close this seminar now. Thank you again, and also see you next JSC seminar. Thank you very much. Yamada Sensei, Nagai Sensei, Nagai-san. Yani-san, thank you. You are joining.
Thank you very much. I cannot open my video.
Yeah, and also, yeah, you have many questions, so your presentation was very nice. Thank you.
Thank you very much. I'm happy to.
Okay. So, 長井さん、先生、とりあえずもうこれで大丈夫ですかね。
Thank you very much,
すみません、
Yanni-san.
ちょっと
Thank you very much, everybody.
You're welcome. Thank you very much.
Thank you. See you next time.
Thank you, Yanni-san.
はい、ありがとう。
Thank you.
はい、ありがとうございます。
Oh. Yes.
But we have recorded that.
Yeah. We can take a screenshot later. Yes.
Later, maybe we can. And also, we need to upload that today's seminar on YouTube later.
Yes.
まあ、コンフィデンシャルがなければ、タイサイド聞いといた方がいいですか？
ちらっと口頭
特に企業の人の発表もあったから。
そうです。
まあ、大丈夫じゃないですか。
多分大丈夫です。まあ、後でまた確認すればいいとは思うんですけど。
はい。わかりました。
じゃあ、はい。じゃあ、僕らはこれから、いや、大島さんと僕はここ帰ります。
はい、ありがとうございます。
ソム先生とお食事するそうです。
お疲れ様でした。
どうもありがとうございました。
ありがとうございます。これも今、もう録画切れてるんですかね。もうオープンじゃないかなってるのかな。
はい。一時停止になってますね、録画。
そうですか。はい。佐々木さんも大変ありがとうございました。
はい。
遅くまで7時
じゃあ、
になってしまいました。
こっちも切っちゃって大丈夫ですか？
お疲れ様です。
はい。大丈夫です。
実際側も切りますよ。
はい。どうもありがとうございます。お気をつけて。
じゃあ、永井さんが北海道に、
はい。
来週から頑張ってください。
あさって引っ越し。はい。動きますので、またこれからもよろしくお願いいたします。
はい、お願いします。じゃあ、お疲れ様でした。
お疲れ様でした。ありがとうございました。
はい、
よろしくお
じゃあ、出ます。
願いします。
はい、どう
あ
も。
りがとうございました。失礼します。私も失礼します。
全部切ります。
はい。